this is an important theorem from your book. It says if I have a function f that is continuous and a function g that is continuous, then the composite of those two functions will also be continuous. Composite, I like to write like that. Some people would do this F-O-G, fog, or G-O-F, goth. I like to do it with the parentheses. Why is this important? It's important because a lot of functions that we have are composite functions, and we like to make sure that they're continuous, especially when we start doing derivatives. So let's do an example. Is f of x a continuous function? Well, I'm going to take f of x and I'm going to make it up into two separate functions. I'm going to call g of x equal to the square root of x, and I'm going to call h of x equal to x divided by x plus 1. So the composite function would be, so g of x, I know that that is a continuous function, and h of x, I know that is a continuous function. So my composite g of h of x is equal to, well, I'm going to substitute h of x in for the argument of g of x. That is equal to the square root of x over x plus 1. So this now I've determined is continuous. How about this function? Is this a continuous function? Well, I'm not sure just by looking at it, but I'm going to make it up into two separate functions. I'm going to call g of x equal to sine x, and that is continuous. And I'm going to call h of x equal to x squared plus 1, and that is continuous. So my composite g of h of x, all I'm doing is I'm taking h of x, and I'm making that the argument of g. So I get that is equal to sine x squared plus 1. So these look kind of simple, and they are, although the idea of what's continuous or not might be a little bit still confusing. But the point is, a lot of times when we're doing things like this, when we're doing calculus, we're going to have to take functions that look complex and deconstruct them. We have to take them apart to be able to look at the pieces, because then we have rules that let us analyze what to do when we put them back together.